Thanks for having me. Sorry I couldn't be there in person. I've enjoyed my visits to Esperance in the past. It's a beautiful part of the world, so I'll try and give you an update of the work that we've been involved with via Zoom here, though, and hopefully you can get the messages all right. So we have been involved with some harvest weed seed meal testing that was funded through SAGIT. This took place back in 2022. It was a culmination of, I guess, a bit of a lead up to that in terms of, interest from the industry and I guess the participants in the meal market to have an independent test and to sort of ratify a protocol for that. So we put an application into SAGIT to support that work, and they were good enough to back it in and fund it, and that's what I'll present to you today. So the way that testing was done was in a controlled environment. So the picture on the screen there is from the grain shed that we had the meals tested in, where we had 3 different meal types, and we were testing them basically driven by the PTO of a tractor and controlling the input of chaff flow and weed seeds and as many parameters as we could to try and isolate the differences in meal types and the parameters that we were interested in. And I'll run through those in a bit more detail. So as I said, this was supported by SAGIT, which is a South Australian Grains Industry Trust. So they collect a levy from South Australian grain growers that they invest into research each year. And generally it's aimed at stuff that has a uniquely sort of South Australian relevance potentially, but in this case it's certainly probably relevant to the grains industry as a whole across the nation. So the groups that were involved in that were the fellas that I work with at Trengove Consulting, so Stuart Sheriff and Jordan Bruce in particular, Stewie in the photograph there. The Condinan Group, Ben White and Mark Saunders, provided some independent observation over the protocol and assistance in that, and also in the publication of the results when they've been released. Adelaide University was involved. Basically, they were undertaking the germination protocol, so each of the samples that were collected from each test were sent to Adelaide Uni, and independently they planted those out and did all the counts on those. And then all the meal manufacturers were also involved in this, and we thank them for their support to get this up and going and supplying the machinery that we needed to perform the testing that we did. So what did we do? To start off with, we had to basically define and ratify a test protocol and the equipment that would be used, and that was in collaboration with all the manufacturers. We discussed the protocols prior to testing, and then they supplied the machinery that we needed, and we then undertook that testing at that location in Balaclava. So testing the meals independently on weeds of Australian significance, in particular annual ryegrass, Lolium rigidum, which is pretty well known probably as the most important weed in Australian farming systems. We included wild radish, and we also included mallow or marshmallow. That last inclusion might seem a little bit odd, but we had a project in 2017, which again was a SAGIT project, and we were working with Seed Terminator to understand how it performed on weeds with a sort of South Australian focus, and some of the weeds that we sort of pick up in our legume phases quite often, and marshmallow was one of them, but it also included bifora, bedstraw, mustard, turnip, tares, and a few others that can be problematic. And medic was another one. Marshmallow was something that we found in that was proved to be a little bit more difficult to control than some of the other weeds, and so we were keen to include that again to see that we could replicate that result and I guess understand how we could go about killing it better. So they were the weeds that we introduced, and yeah, these are the seeds. So this was marshmallow, that's the ryegrass, and that's the radish. Things that we were looking at in terms of factors that might impact meal performance were meal wear. So each manufacturer was asked to supply a meal in new condition, and also a meal in what they considered close to end of life condition, which is probably fairly subjective, but it was the protocol that we came up with, and so that was done. The reason we're interested in that is because, most of the testing is done on new machines, but the machines are generally only new for a certain period of time, and they start to experience that wear, and that's a continual process until it reaches that end of life state. And there's probably a response to wear across the life of the machine, but we were sort of interested to see what the performance was at the start and end of that process. So we looked at mill wear. We also looked at mill speed, which I think the guys there will probably tell you that the mill speeds that we looked at sort of full recommended RPM rates versus a 90% RPM rate, which I think would be quite low to experience that in the field in reality, but it was something to do to sort of pressure test the different machines. And it was looked at in an overload scenario. We had a high flow rate of chaff, and also a slower mill speed, which might occur on the rare occasion where you overload the machine and you have a heap of chaff going through, and the mill may slow down for a brief period of time. So to just understand what happens in that sort of scenario. The final thing that we looked at was the in-feed rate, or chaff flow rates, the amount of chaff that's being processed by the mill at any one time. So the chaff feed rates that we were looking at were rates of 1.5, and 2 kilograms per second. Now this is going into 1 mill. Obviously, out the back of the machine, you've got 2 mills operating, and so the flow rates are going to be twice what I've quoted here. But in terms of 1.5, and 2 kilos per second of chaff going into a single mill, roughly we think it equates to about 36, 54 or 72 tonne an hour of grain harvest flow. Now, it's not a hard and fast rule. That's based on a chaff to grain ratio of 20%. So for every tonne of grain that is being harvested, there's sort of 200 kilos of chaff coming through the system. And it's not hard and fast. It could be up to 30% of the grain flow as chaff flow through the machine. So, but that gives you an indication. We've got that range there to cover sort of a range of scenarios. So the chaff material came from a farmer near Balaclava who has a chaff cart, and he bales his chaff heaps for use in a feedlot, and we got access to a couple of those bales. So there's a bit of mixing that goes on through the process of collecting the chaff in the chaff cart, dumping the chaff. They then push those heaps out into rows before then baling them up with a crone high density baler. So there were some weed seeds contained within that chaff, including ryegrass, and I'll discuss the results from that in a moment. But it's important to note that the ryegrass in that background chaff was lighter than what has been used in testing previously. So the seeds in that background chaff weighed 2.1 milligrams per seed, and I'll discuss that in a bit more in a moment. But we also added seeds to the tests as well, which I showed you before. So the mallow, the wild radish, and the ryegrass that we added. But the ryegrass we were adding was heavier. It was 2.9 milligrams per seed. So you can see there's a difference there of about 38%. The seed that we're adding is sort of more in line with ryegrass seed that's been used in testing previously, whereas the background chaff had this lighter ryegrass seed in it. The test duration lasts for 3 seconds, and the seeds that we add, we mix into the chaff in the sort of middle 1.8 seconds of the test, so that as those added seeds are entering the mill, basically the mill's running at capacity in terms of chaff flow, and there's less opportunity for direct steel on weed seed impact that isn't replicating what was happening in the harvester. So adding the seeds in the middle of the test. We then process that. So that's processed through the test stand, where the belt is feeding that into the mill at a constant flow rate. That's ejected out onto the floor, as you can see in that photo. We then get busy with brooms and blowers and collect all that material back up. And when we were sticking 3 kilos through the test for a 1 kilo per second test, we were getting within about 50 grams, 100 grams of that 3 kilos back. The rest was dust that got lost up in the rafters. So we collect all that material up and then we subsample that. So we put that through a rotary subsampler, which gives us a representative sample out of that test. And that subsample was sent to Adelaide Uni for germination in soil in an open air environment during winter to overcome any dormancy issues that might be encountered with ryegrass in particular. And when any weeds emerged, they were counted and removed from the tray. And that process was repeated every couple of weeks for 11 weeks until we were satisfied that the majority of weed seeds had an opportunity to germinate. So I've just chucked this slide in, which is fresh off the press, fresher than even the other results that I'm going to share with you. We've been interested in this since getting the results from the testing. We've been interested in this impact of ryegrass seed weight and what that might mean for the performance of the machines, and I'll give you the results of that in a moment. But just to put it in the context of how heavy ryegrass might be in the paddock, we got a range of samples from Peter Botsalis at Plant Science Consulting, samples that have been submitted to him for resistance testing, and he was able to grab a little subsample of each of those samples and set them aside for us. And we haven't counted them all yet, but we're in the process of counting and weighing those ryegrass seeds to understand the weights of them. And so these are all the little packets that Peter's put aside for us. And my poor niece that's about to start uni, I had her in here the other day starting the process. She counted about 7,000 ryegrass seeds by hand and weighed them each. And she hasn't been back since. I think she's waiting for uni to start pretty quick. But what we learned from that is that there's a distribution of ryegrass weight that we encounter in the paddock. And this will probably shift from season to season. But for these 38 samples from South Australia and Victoria, this is the distribution in seed weight that we saw. So here I've broken it into segments. So on the left-hand side, you've got seeds that weigh less than 1.5 milligram per seed. And then each increment increases by 0.25 milligrams per seed. On the right-hand side, you've got the number of samples that exceeded 3 milligrams per seed. So what we can see there is that the median weight of the ryegrass seed that we have measured there is 2.38 milligrams. The seed that was in the chaff was 2.1 milligrams, so that sits there. The seed that was added was 2.9 milligrams, so that sits there. So probably the next time some testing's done, we should get some 2.35 milligram seed and test that to probably get the most representative of what's in the paddock. And also we'd like to test the range of different seed weights to see how that responds to seed weight. But why does seed weight matter? Well, I'll cover that now. So I'll throw up the results here of the ryegrass kill for the background seed only. That was 2.1 milligrams per seed. For the iHSD, the Seed Terminator, and what we're calling the HC Seed Terminator there is the high capacity Seed Terminator option. So the results there indicate that the Seed Terminator was giving 92% control of that background ryegrass seed, whereas the iHSD and the HC Seed Terminator were 82 and 81%. We were able to determine the control of that background ryegrass seed on its own because we had tests where we just run the straight chaff through without adding any ryegrass to it. And so we could compare the amount of ryegrass that germinated from that test with the same quantity of chaff germinated on the trays that hadn't been processed and work out the percent control. And so, yeah, there's that sort of 10% difference there, which in the samples that we had on the trays, there are about 555 ryegrass seedlings that germinated in this test. And so when you're getting 92% control of the Seed Terminator, that's leaving 44 ryegrass seeds that germinated. For the other two, it's closer to 100 and 105 seedlings per test that germinated out of that 555. So that's the result for annual ryegrass control for the seed that was present in the chaff. This next slide here is looking at the relationship between how much energy was consumed during the test and the level of control that we achieved of annual ryegrass. Now, the results I'm going to refer to going forward are now the combination of both that background ryegrass seed that was in the chaff and the ryegrass that we added to that chaff. So both seed sources are included in these results going forward. This graph here is representing the performance of different meal configurations at 1 kilogram per second at the full recommended RPM with new meals. What it shows is that even though there's a few different meal configurations on there, there's this relationship between power consumption and control that seems to fit through those different machines. And there's this relationship that we can't ignore, and that is that to get high levels of control required more energy to be consumed and impacted into the seed to achieve that level of control. Now, this is looking at just the energy consumed during the test. It's taken out any energy required to run the mill empty. So this is just energy that's going into the chaff and the weed seeds. I guess the other thing to notice about that is that it's not linear, this relationship. It's steeper at the start, and then as you get closer to approaching 100% control, it flattens out, indicating that to get that last 5, 10, 15% of control is using a reasonable amount of energy to get to those higher levels. So in this slide here, we're just looking at the relationship between energy consumed and the chaff flow rate. And it's not surprising, I don't think, that with more chaff going through the mills, the more energy that's required to process that chaff. And you can see the differences between the mill types there as well, where we've got the Seed Terminator in the orange, the HC Seed Terminator in the grey, and then the iHSD there in the blue. All right, so I'll get into unpacking the results for the different meal types and the different factors that we tested. This is a busy graph, and I'm going to break it down in the next few slides to pull out the important differences, but this is just showing you the full suite of results across the iHSD, the Seed Terminator, and the HC Seed Terminator there, where the first 5 bars relate to the iHSD. The bars 6 to 10 here relate to the Seed Terminator, and bars 11 to 15 relate to the HC Seed Terminator. And then we've got the same 5 treatments represented within each of those mills. So the first 3 bars are looking at the effect of chaff flow rate on ryegrass control. So 1, 1.5, and 2 kilos per second. Same for the Seed Terminator, 1, 1.5, and 2 kilos per second. And then the HC Seed Terminator, 1, 1.5, and 2 kilos per second. The 4th bar is looking at the effect of slowing the mill down to 90% with a chaff flow rate of 2 kilos per second. So this is comparing bar 3 with bar 4 here. Same here for the Seed Terminator, and same here for the HC Seed Terminator. And then the last bar is back to 1 kilo per second flow rate. Sorry, the 5th bar here, 1 kilo per second flow rate at full RPM, but with a worn mill. And this is the worn Seed Terminator, and this is the worn HC Seed Terminator. Now, it's sort of hard to look at like that, so I'll just pick that apart a little bit more. This is just showing the same data, but in a table format. And this is presented in the Kindinan Farming Ahead magazine as well, with the article that was published in there. But just, I guess, summarising or looking at some of the bigger trends here. Across the bottom here, we're averaging the control across all of these 5 treatments for each mill. So the average across all of those 5 treatments for the iHSD was 70, as it was for the HC Seed Terminator. The average for the Seed Terminator was 90%. This is, again, for ryegrass control only. If we average across the different meal types for the treatments, we can see the effect of those factors reasonably clearly. So these first 3 rows here are looking at the effect of chaff in feed rate again, so 1, 1.5, and 2 kilos per second. Here you see the average across those 3 mills was 90, 84, and then 74% as we increased chaff flow rate. When we slowed the mill down to 90% at that high flow rate, the average across the 3 machines was 57. So you can see the effect of that mill speed drop in control there. And lastly, again, averaging across the 3 mills, we can see that there's this general trend that the worn mill is dropping control compared to the brand new mill at 90% average is dropping sort of 12% on average. So these next few graphs are just going to pull that data out in a bit more clearer fashion, I think. So this is looking at the effective chaff in-feed rate at the bottom, so going from 1 kilo per second up to 2 kilos per second. On annual ryegrass control for the 3 different meal types. In the orange, we can see the performance of the Seed Terminator. It does decline slightly, but not as steeply as the other meals tested. Here we can see that the iHSD and the HC Seed Terminator have a similar response curve to that increasing flow rate. And in all the tests, we couldn't actually separate those two statistically. They sort of perform the same. Okay, moving on. Now we're looking at the effect of meal wear. So down on the left-hand side there, we've got some percentages in terms of the meal wear, or the amount of weight that was lost from those wearing parts for each of the meals that we were testing. So on the iHSD, the stator was still new, but the rotor had lost 22% by weight of its wearing impact parts. The Seed Terminator, the stator had lost 27% by weight. The rotor had lost 25% by weight. And the HC Seed Terminator, the stator had lost 11% by weight, and it was the same rotor as the standard Seed Terminator, which had lost 25%. So that was an attempt to get a measure of meal wear by just weighing the components. What we found is that that hasn't really related to the differences in control that were achieved with the different meals. And so perhaps there's a better measure of wear that we should be looking for that better explains what's happening in terms of the ryegrass efficacy. But if we look at the results here, yeah, you've got iHSD there on the left, where there's a reasonably significant drop-off in control with the worn rotor there. And then, yeah, still moderate drop-off with the two Seed Terminator mills as well. The next thing is, yeah, just picking apart that effective mill speed again. So the 100% RPM treatment was running at the recommended operating speed, which for the iHSD was 3,050 RPM, and for the Seed Terminator, 2,950 RPM. And then the 90% RPM was 90% of that value. So here we can see what happens when we slow the mill down by that 10%. There's a fairly consistent trend across the board there that control drops off. The standard Seed Terminator probably holds up a little bit better than the HC Seed Terminator and iHSD in that test. Again, the 90% sort of RPM, unlikely to be experienced in the field, but just pushing the limits to see how the different machines hold up. Finally, we included a couple of extra mills in the testing, but only for one of the tests. So the blue bars here are the iHSD, the Seed Terminator, and the HC Seed Terminator, which we've been talking about for all of the other results throughout the presentation. And here we've included the iHSD with the high flow stator and the MIDI Seed Terminator. This was for the 1 kilo per second flow rate and new mills operating at 100% of their RPM. And yeah, we can see where they sort of fit in relation to the other results. So the MIDI Seed Terminator is probably appropriately sort of named there because it sits right in the middle of the Seed Terminator and the HC Seed Terminator. And the iHSD with the high flow stator dropped off a little bit from the standard high iHSD, but not actually significantly different from the iHSD. Okay, just looking at other weeds now, I won't actually present any results on wild radish. The reason being, and it's a good news story in this case, is that all the mills performed exceptionally well and provided near enough to 99% control, and there was no difference between mill type or any of the other treatment factors that we imposed, including flow rate, mill speed, or mill wear. So yeah, in this testing, the radish was controlled really well. Here I'm presenting the results of the marshmallow. And I'm just going to present the averages across the different meal types here, basically because the interactions between meal type and the other factors that we tested weren't significant. So I'll present the average of this is the average of the meals across all of the different parameters that we tested. So across the different flow rates and meal wear and meal speed. And again, the Seed Terminator performed relatively better than the other two meals in this example, where they've given 86% control. And again, we weren't able to separate the HC Seed Terminator and the iHSD, where they were 74 and 69%, but not significantly different. So that's that. And then the effect of the different parameters on marshmallow control when averaged across the three meals. So the top three rows here, we're looking at increasing chaff flow rate here. So going from 1 to 1.5 to 2 kilos per second. Again, we see that chaff flow effect on efficacy of marshmallow, where it drops off by that 10% from 84 to 74% on average across all three meals. When we look at the effect of meal speed dropping from 100% to 90% with a 2 kilo per second flow rate. Again, we're dropping another 9% with that lower meal speed, and the wear effect with a 1 kilo per second flow rate and full meal speed is comparing this number here to the 84 at the top. There's a trend there that it drops off, but they're not actually significantly different. So that's all the numbers. So I guess, yeah, the conclusions there are some differences in commercial meal performance for a couple of the weeds that we tested there, ryegrass in particular and marshmallow as well. There's a relationship there with power consumption that we can't sort of ignore. There's good radish control across the board, yet the ryegrass and marshmallow were more difficult to control and more responsive to the different factors that we tested, like the flow rate and speed and wear. The results were responsive to those factors, the chaff load, the speed, the wear. And we also think that the weight of the ryegrass is important, and we think that there's more work to be done in that space. We've put an application to SAGIT to do some more work in that area to explore that in a bit more detail, and yeah, it'd be interesting to unpack that more in the future.